Okay, first thing I'd like to do is see if there are any questions on the project, any clarification you need, or things like that. I've had visits from a couple of students in the online course section of this course, and I know a couple of the questions they had. Have you guys done anything with it yet? Look, any questions? Okay. The thing to realize about this project, what we've done over the past few weeks, couple of weeks, has been to take a pretty standard problem that we'll end up with, designing a system, and break down the parts of it and focus on how we use antennas in that. And so when I showed you how to calculate free space path loss, that was one piece of it. When we looked at link budget and the math associated with that, that was another piece of it. When we worked through the problem together, it wasn't actually an assignment, but that problem that we worked through together, and I showed you how to analyze and compare antennas, that was another piece of it. What the project does is basically take all of those, put it into a problem very similar to what you're going to have to do out in the field if you get into any of this sort of stuff. It's not as nicely laid out as the problem we worked through together. I don't give you feed line loss, but I do give you the key pieces of information that you typically have. And the whole goal on this is to get it so that you're comfortable working through a design solution like this. You have location of sites. You have to figure out Fresnel zone. You know the operating frequency, so there's Fresnel. From the two locations, the Fresnel zone calculator will give you distance. So now you can do Fresnel zone size, which lets you know how tall your towers have to be. You can do path distance, which, along with the frequency, lets you figure out what your path loss is. Now you know enough to do that same type of analysis. Now there's some different assumptions. For example, this problem is laid out instead of 3 separate links. You have one central radio, think access point is actually what I'm modeling it on. I'm just not using that term. And you have multiple paths back to that one radio. And makes your design process a little different. Okay? Couple of things to note. There is not one correct solution to this. There are several ways, given the information I've given you and the antennas I've allowed you to use and the feed line and all that stuff. There are several ways that you can solve this problem. You're not trying to guess what I'm going to do. What you have to get used to in here, and this is the piece, this is where students, once you hit the 300 level, start getting a little uncomfortable, because the questions stop being, here's what we're doing, here's the calculation, what's the answer, and start being, here's the math, what does it mean? Interpret it in a real world. Math is a tool. We use math differently than engineers do. Neither one's right or wrong, it's just different. We're not as worried about decimal places because that's not the way our work goes. Okay. So in this class, if you look through the rubric, yes, I'm going to grade your math and make sure that you did it well. There are points for making it correct. Everybody ought to get those completely. The big piece that I'm going to be looking at is, okay, here's what the math says. What did you choose for an antenna and why? Okay. The reason I limited you to one page, when you're proposing something in business, you're going to lose even technical people after one page. Now, that doesn't have to include all your calculations. In fact, I don't want it to. I want those fully laid out just as an attachment. But you need to be able to summarize in this. For this project, I'm letting you use all the technical language you like. Person who's reading this is a technical person. You don't have to translate it into management speak. It still needs to be well written. This is still a record of your work, so it needs to be well written and present your information clearly, concisely, and in a logical way. Okay, so there is writing to it. You just don't have to translate it into non-technical terms. Okay, you will have to later on. Trust me. You have to get comfortable with that idea. I'm sorry? Your writing needs to match your audience, and I've specified an audience. Okay, so if you can do that explanation without using a lot of technical terms, great. That's fine. You know, being able to. My wife's a speech pathologist, so her term for this, she's also the best teacher I know. Works for me. When I was talking through this assignment, she said, well, you're talking about something called code switching. Can I change the way I do the vocabulary I use and the way I present the same information depending on who I'm talking to? And we're going to practice that because it's something you have to know. By the time you get out of here and start looking at jobs, you've got to be able to do that, because you're going to present very technical stuff to people who don't know what you're talking about when you start speaking in three-letter acronyms. Yeah, I mean, it's just a skill for this business. That's probably the most uncomfortable thing for our students at the 300 and 400 level, is we start requiring that. The other thing to keep in mind is that you have to keep in mind the value of math. Math tells you predictions to the best of our technical ability. Math doesn't tell you what the solution is. You have to interpret it. Your interpretation is just as valid as anybody else's. It's not as practiced yet as it needs to be. And so what I'm asking you to do is take the math, whatever you decide to do on that antenna solution, that's fine, back it up. This is a class. My job is to make you think, so I guarantee you whatever you say, I'm going to find something to ask you about it. I'm not going to say it's right or wrong, but I am going to ask you about it. Okay? That's the way I get you to think through these things. Okay? So I'm not picking on you. I just want you to think through it. And if I can make you think through it twice, I've done my job even better. Okay? I would like you, I made the project due since we were a little later getting started on it than I had intended. The first deadline on it is Friday morning. If you have specific questions, it'd be really good if you could do those by Wednesday. I'm going out of town Friday, so I'm not going to be available for afternoon office hours. The project is due at 8 a.m. Friday, and I'm going to try to get it graded before I go. Suffice it to say, if you come to class Wednesday with some questions or come by during office hours, that'll get you well down the road. Okay. Anything further on the project, the way I'm looking at it, or anything like that? Okay. What I want to do today. The slide is labeled for Chapter 5. It's actually more of a look kind of at an aspect of the rest of the semester. And I want to be a little deliberate about this, and that is how we're going to approach specific protocols. If you look at the rest of the chapters, with a couple of exceptions, they're all about specific protocols or specific network types within which we talk about specific protocols. This one, Chapter 5, happens to be about personal area networks, so by definition we're talking about something that's very short range, meaning very low power, meaning simple, small antennas. We're going to talk about metropolitan area networks. Okay, there's a different range combination. We're accomplishing something different. Okay? This is not just a technology class. This is a how we are technologists and we apply these things to solutions. Some of the chapters will have to do more design than others. I don't know of anybody who really is the Bluetooth expert for a company, for example. Bluetooth is typically that kind of thing you buy, and that's about it. and I'm using the examples out of this chapter. Zigbee, for example. Have any of you guys messed with Zigbee? Actually, you're more likely to have coming out of EMT. Zigbee is a short-range network that is designed for instrumentation, and it is made to develop custom buses. First place I saw it was in a high-altitude balloon package that had 4 different boxes trailing about 50 feet behind a balloon, and that's the way the different modules communicated, was with Zigbee. So pretty neat stuff. Again, short range, had specific applications. We're going to look in here, we're going to relate them to the OSI model. Now, your book does this, and it actually does a pretty good job of it. It's one of the reasons I liked this book when we were looking for text for this class. Parenthetically, choosing a text for this major is really hard. Our 50-50 mix of business and technology means we typically end up looking at a subject from the business and technology level, and you either find engineering texts, which are way deeper into the technology than we want to go, and honestly, usually not very practical, or they're technology for dummies books, radio for idiots, if you will. We need stuff in the middle, and that's one. I was happy with this book. There's some things I don't like about it, but I've never used a book that I was real happy with. So anyway, that's why I'm careful to point out what I'm doing different than this book. I do like this book. It's just, it doesn't do everything we need. It's a pretty good match. It's not a perfect match. The OSI model you guys have dealt with for a long time now. You thought you were safe. This class in particular, several of them, as you go up, particularly through the wireless part of things, deal almost exclusively with layers 1 and 2. We're going to make, because of the standards organizations, remember we talked about standards, IEEE got involved in data networking very early on as one of their key places they wanted to play. And they started Project 802. Ring a bell? Okay, yeah. Ethernet, for example, is 802.3. Token ring was 802.5. Anybody know what 802.4 was? Trivia question for the day? It's token bus. A bus network like Ethernet that used token passing. The reason we use these models, of course, is to facilitate talking about how this communication works, and so that we can design modular solutions to this. In other words, I can design a solution to the things that have to happen at layer 3, and I really only have to worry about a little bit of what happens at layer 4 because I've got to hand information to it, and a little bit of what happens at layer 2 because I've got to hand information to it. But mostly I deal with what I want to do. Okay? Project 802 took on the task of documenting and promulgating standards for accomplishing particular types of networking. 802.3 is one we've talked about. So what do you do when we're looking at 802.whatever for wireless network, 15 for personal area networks, 802.11 for wireless local area networks? What do you do when there are lots of variations in that, and what do those variations mean? Okay. From a technical point of view, we need to know the differences because this is what we do. From the business point of view, we need to know the differences because we need to choose the capabilities that best match what our business problem is or what our environment is. So either way, we need to be familiar with these. Now, the example I used of Ethernet, we have an Ethernet card. Okay. What do we mean when we say that we're going to look at layer 1 and 2? Well, Ethernet's been around a long time. In fact, Ethernet started out on coaxial cable, which predates, I think, probably everybody in the room but me. you ran a coax about the size of your thumb down the middle of your halls. There's still some of it buried in our ceilings. And whenever you got close to a computer that needed to network, there was this big old, it was called a vampire tap, and it was about half the size of a cigar box, and you literally clamped it on the cable, and it penetrated through and made contact with the shield and the center conductor. We started getting, that was in the early 70s, you know, a small computer was only a couple of racks. We started getting smaller and smaller computers. Processing power went down. The use of it went up. And by the time you got to the end of that decade, you had affordable computing on the desktop. Instead of running a thick cable, we went to a smaller cable. Okay? Smaller coax, which is what I'm actually showing here. And you've seen on some of the devices we get, occasionally you'll still see a BNC coaxial connector on the back. That's 802.3. 802.3, and I can't even remember the sub-piece. It's 10-base-2 is the name of the protocol. So what are we saying in here? Because here we have a network adapter that has both a coaxial interface and a twisted pair interface. Okay, here's what's going on. 802.3 is trying to specify all of the function of the physical layer and the data link layer for the Ethernet standard. So, for the layer 2 part, layer 2 is responsible for taking the data that comes down from upper layers, packaging it for transmission, and handing it to layer 1. Layer 1 takes that package, it's actually called a frame at layer 2, and sends it bit by bit across the network. And I mean literally bit by bit. Layer 1's job is to represent bits. Now, we've gotten good enough at this, and you did problems earlier where we can actually represent multiple bits with one symbol. Remember, we can code more than one bit per symbol. But the idea is still layer 1 focuses on bits. Okay? So to deal with that complexity, the 802 project actually subdivides layer 2 and layer 1. Layer 2 is divided into an upper and lower half, the media access part of it, and the logical link control part. Okay? Those two accomplish different things, and we're going to look at how they vary. It actually subdivides the physical layer. Let's use Ethernet as an example. Both coaxial-based and twisted pair-based Ethernet, I'm assuming 10 megabits. I know it's ancient history, but that's the easiest way to talk about it. Both coaxial cable and twisted pair use the identical frame. They use the same Ethernet frame. So layer 2, the upper level of layer 2 is the same. The lower level of layer 2 deals with how we share the medium. Now, Ethernet defines a way of doing it. Remember, CSMA, CD. But look at the difference. Here, we have a coaxial cable with lots of machines connected to that single physical piece of media. In twisted pair, you can't make a bus network in twisted pair the way Ethernet uses it. You have to use a central device, a hub or a switch. Well, that means sharing has to work differently. We can still use CSMA CD, but we have to kind of change the rules about what that is. So that's why there are two halves to layer 2. Similarly, coaxial cable has one physical set of characteristics. This happens to be something called 10-base-2, which uses RG58 coax, about the size of a pencil, and BNC connectors. It specifies how we're going to signal a bit. It's a voltage change between the center conductor and the shield. It specifies how far we can run that signal. 10-base-2 means we can run it 200 meters of cable. It specifies all that sort of thing. So that is one of the subdivisions of the physical link. What's the other one? What's a bit? Either way, we have to define a bit that works with this because we have a timing thing going on between these two layers. So we've got a pretty complex problem, even dealing with something as simple as a wired solution. This is why you have so many different 802.11 Wi-Fi protocols. First off, we introduced it as an easy way to get a little data off the network, and it just exploded. You know, everybody in the world is carrying around something like that, or a phone, or whatever. More users, more network usage time, and oh, by the way, we're moving ever bigger files. You know, the window of what's a small file just keeps getting bigger and bigger and bigger. And so, periodically, we have to make this run faster. Okay? That's where all your changes in the 802 specifications are driven by. Wireless networking will tend to treat these two as one thing, and that's how we refer to it. I'm doing it right now, 802.11. Now, how do we separate those types? We put a suffix letter, 802.11a, 802.11b, 802.11g, N, AC. Now we're starting to use 2. All of those are differences in how we accomplish the tasks at these two media. In this class, our focus is going to be outlining this, and your book does a pretty good job of how the different protocols actually do these. So I'm mostly going to leave that to your reading. What the book doesn't do as well is look at what difference that makes in how we apply this practically. And that's what we're going to focus on in here. When I bring in the summary lessons, I'm basically going to assume that you've read the chapter, and if you have questions on it, we can discuss it. But my focus is going to be, okay, now that we know these things, how does that affect what we do as technologists, whose job it is to take this and make it come out over there? You know, take this data, get it over there. Okay? We're going to do that with each of the networks coming up. This class, until this semester, has not had a physical lab component. I'm going to change that, and for that reason, I'm going to take chapters out of order. I mentioned this last time, but let me outline this a little more fully. We are going to do Chapter 5, and then we're going to skip to Chapter 8, and we're going to deal with, we're going to skip to Chapter 9. We're going to deal with metropolitan area networks, wide area networks, and RFID, pretty much like we're dealing with PANs. You know, we're going to talk about, we're going to look at applications. None of those are things where we are likely to actually implement it. If you do, that's great. It's just not where most of our people get hired. Those are, for implementation, are usually engineers or end users. They don't need a middleman in either case. Our job, where we actually implement stuff directly, typically falls in a couple of places. 802.11 Wi-Fi type access, we typically do directly. For that reason, I'm going to do a significant lab component on that. We'll do several labs looking at how we put this together. We'll look at the theory. I'm going to extend it a little bit. The other place we directly deal with things is in satellite links. Other than talking about a little bit in the wide area in that chapter, I'm not going to deal much with it because we're not going to do a lab component on, because you're not likely to directly deal with it. Typically, you have a satellite link that's available on a network, and you decide how you use that as an application. We'll talk about the difference. The biggest problem with it is latency, and throughput's a problem too. So the lab is going to focus on 802.11. We'll probably start labs around the 1st of November, something like that. I'm hopeful. We'll do them physically in here, but I'm hopeful that they're going to be completely available online. In fact, I'm wanting you to test that. So, because I can fix it. If you guys in the local class find something wrong with it, I can fix it so that the people in the online class can do that. Okay, so that's kind of where we're going with things right now, and I just wanted you to understand the path I'm taking with it. At this point, I know you guys can read. I know you have enough technical background to understand the chapters in here. You know, you don't need me to interpret words and stuff like that. I'm glad to fill in any blanks you do come up with, but I trust you to be able to keep up. You are responsible for stuff in here, and we'll still have exercises and quizzes and such as that. It's just what I cover in here is mostly going to be supplementary to this, more so than it has been so far. Okay? Questions on that? You okay with it? Okay. If you would please, before Wednesday, at least look over the problem and see if you have any specific questions on it. Thursday I'm here, but I've got a couple of meetings already stacked up, so it's going to be a little iffy catching me Thursday. So, okay? See you Wednesday. Please read Chapter 5 before you come in Wednesday.